Hello, everyone. Welcome to Pre-Lecture 15. So we'll start Unit 3 for us, looking at Chapter 14 in our textbook, which has to do with acids and bases. Okay, so let's jump right in. And so acids and bases and their subsequent chemical reactions sum up or make up some of the most important reactions on Earth. And so if you think about just water itself, if you were to break it into its smaller parts, it would consist of protons, what we would just identify as H plus, as well as hydroxide. And so we have multiple ways that we can define acids and bases. One of the most common ways that we'll use in this unit especially are called Bronsted-Lowry acids and bases. And so a Bronsted-Lowry acid will donate a proton, and a Bronsted-Lowry base will accept that proton. And so in our example here, our water is acting as a Bronsted-Lowry acid. It is donating one of its protons to ammonia, which is our Bronsted-Lowry base, in order to form our conjugate base and acid, which we will go through specifically what those mean in just a moment. Okay, and in fact, let's do it right now. So it can be useful to think of acids and bases in conjugate pairs. And so anytime we have an acid-base reaction, we would identify our acid and our base on our reactant side. And then on their products, we're also going to have a conjugate base and a conjugate acid. And so, for example, here we have water reacting with ammonia, and water, as we said, is going to be the acid on the reactant side. And that means if it's an acid on the reactant side, it will be a conjugate base on our product side. And then our conjugate acid on the product side will, of course, be our base on the reactant side. The reason this is important is, of course, because these reactions are in equilibrium. And so we have our products, and they can react a separate acid-base reaction to go back to reform our reactants. And of course, they would perform this acid-base equilibria. And so I hope you feel like you learned everything from chapter 13 well with equilibrium, because we're just going to continue to build upon it in chapter 14 and 15. Okay. And so that's one example. We have some other examples here. And so if you'd like to take a moment, you can pause the video and identify what is our acid, what is our base, and then which of these molecules will be the conjugate acid and the conjugate base for each of these reactions. Okay, so if you'd like to pause the video, you can do that. But here are the answers. So in our top reaction, we have HF, hydrofluoric acid, reacting with water, donating a proton. Again, H2O would be our Bronsted-Lowry base here. And then our H3O plus, which is a molecule called hydronium that we'll be talking quite a bit about this semester, is our conjugate acid, and fluoride is our conjugate base. Okay. In the second example, we have water again, but this time it is reacting with a base called pyridine that has this structure here. And this time water is acting as an acid and pyridine is acting as our base, right? So to contrast these here, we can see that water is an acid in the second reaction and a base in this first one, okay? And that brings about one of the interesting properties of water. Is it is a molecule that we would identify as amphoteric. What that means is that it can behave as both an acid and a base. It's one of the things that makes water so special. And so one of the key reactions then with water is called its autoionization. And so this is essential to water's amphoteric behavior. If we think of this in terms of an equilibrium expression, if we have pure water, it will actually react with itself, where one molecule of water will act as an acid, one molecule of water will act as a base, and then we end up forming hydronium, H3O plus, and then hydroxide, OH minus. Okay? We can express this in an equilibrium term, of course. If we were to put our products over our reactants, our products are soluble ions, and then our reactants are pure liquids, water. So our expression Kw is going to be equal to our concentration of hydronium multiplied by our concentration of hydroxide. Okay. All right, and so once we identify our concentrations of hydronium or protons, those are the same thing, and I will be using them interchangeably throughout the semester. So once we identify our concentration of hydronium, hydroxide, um, if those proportions are equal, then we would call our solution neutral. If we have a greater concentration of protons than hydroxide ions, then we would call the solution acidic. And if we had more hydroxide than our hydronium, then we would call it basic. Okay. And so we typically express this with a property called pH. And so pH, of course, can be represented mathematically. And we would do that by taking the negative log of the concentration of hydronium in an aqueous solution. And so again, this pH is equal to negative log of our concentration of H3O+. We can take the inverse function, so undo pH to get our concentration of hydronium. So if I were to give you a pH value, you could be able to find the concentration of hydronium by doing 10 to the negative pH. Okay. Alternatively, we can do essentially the same thing for hydroxide. So if we take the negative log of hydroxide, it's a property called POH. And then we can, of course, determine the concentration of hydroxide if we only know the POH by doing 10 to the negative POH. Okay. And so hopefully you can kind of notice here, basically anytime you see a lowercase p preceding a chemical, that just essentially means take the negative log of the concentration of that chemical. And so we might see some other p functions this semester, but pH and POH are the main ones. Okay. We can also interconvert between pH and POH using our Kw expression. And so Kw is, as we previously defined, our concentration of hydronium multiplied by our concentration of hydroxide. We could say that our pKw is going to be equal then to our pH plus our POH. And that actually has a numerical value that we set, and that is 14. Okay. And so in neutral water, that's going to be pH 7 or POH 7. And in neutral water, our concentration of hydronium will be equal to our concentration of hydroxide. If we were to put a molar concentration to that, each would be 1 times 10 to the minus 7th molar. Okay. Right, and so from that, we can then derive our pH scale. So I'm sure most of you have heard whether things are acidic or basic, they're often identified by their pH. And so this chart from your textbook does a good job showing you both the concentration of hydroxide, concentration of hydronium, how they're essentially inverse to each other, always adding up to 10 to the minus 11th, or minus 14th, I'm sorry. And then our pH and our POH are also always present, always adding up to a value of 14. I'll also point out here that you can have negative pH values. You can also have negative POH values for things that are very basic or very acidic. Okay, and then here are some examples. Things that are more acidic, of course, on the top of the chart here, and then things that are slightly more basic towards the bottom. Okay. All right, finally, just a summary table here. This also from your textbook. When something is acidic, that means that we have a greater concentration of hydronium than hydroxide. Our pH will be less than 7. Things are neutral, of course, they will be equal, and we'll have less hydronium than hydroxide when things are basic at pHs greater than 7. Okay. Hope that was helpful, but if you have any questions, of course, please feel free to email or let me know in class. Hope you have a good day, and I will see you soon.